first law of thermodynamics. Today we shall study about the first law of thermodynamics. In this, the internal energy U of a system can change through two mode of energy transfer. कहने का मतलब है, it means to say that heat can be transferred through two modes, or internal energy can be transferred through two modes. First mode is heat and second mode is work. Let delta Q is equal to heat supplied to the system by the surroundings, and delta W is equal to work done by the system on the surroundings. Delta U is equal to change in internal energy of the system. Now we consider the general principle of the conservation of energy implies that delta Q is equal to delta U plus delta W plus S. Delta Q without delta U plus delta W, that is equation number 1. The energy delta U supplied to the system goes in partly to increase the internal energy of the system, delta U, and the rest in work on the environment, delta W. Equation 1 is known as the first law of thermodynamics. It means to say that heat supplied to the system is creating two type of matter. The first matter is internal energy. Second is work done happen. So delta Q is equal to delta U plus delta W. It means to say that heat create change in internal energy and do some work on the system, and do some work on the system, on the surroundings by the system. So delta Q is equal to delta U plus delta W. Therefore, delta Q minus delta W is equal to delta U. It is equation number 2. The system may go from an initial state to the final state in a number of ways. For example, to change the state of gas from P1 V1 to P2 V2, we can first change the volume of a gas from P1 to V2, keeping its pressure constant. It means we can first go to the state P1 V2 and the change pressure of the gas from P1 to P2, keeping volume constant, to take the gas to P2 V2. Alternatingly, we can first keep the volume constant and then keep the pressure constant. Since B is a state variable, delta U depends on the initial and final states and not on the path taken by the gas to go from one to other. However, delta Q and delta W will depend on the path taken to go from the initial to final states. From the first law of thermodynamics, it is clear that delta Q and delta W is path independent. This shows that it is a system, that if a system is taken through a process in which delta U is equal to 0, then the heat energy is equal to the work done. Therefore, heat supplied to the system is used up entirely by the system in doing work on the environment. For a gas in a cylinder with a movable piston, the gas is moving, the piston does work, since force is pressure times area, pressure times area, and area times area time dependent to volume. Work done by the system against a constant pressure P is delta W or P delta V. Therefore, delta Q is equal to delta U plus P delta V, where delta V is the change in volume of the gas. Now the specific heat capacity. We define heat capacity of a system to be S rho delta Q or delta T. We expect delta Q and heat capacity S to be C, proportional to the mass of the substance. Further, it could also depend on the temperature. It means a different amount of heat may be needed for a unit rise in temperature at different temperature. To define a constant characteristic of the substance and independent of its substance, we divide S by the mass of the substance m in kg. So a small s is equal to S by m is equal to 1 by m delta Q by delta 2 T. That is equation number 8. S is known as the specific heat capacity of the substance. It depends on the nature of the substance and its temperature. The unit of specific heat capacity is joule per kg per Kelvin. If the amount of substance is specified in terms of moles, mu, instead of mass, m in kg, we can define heat capacity per mole of the substance by C or S by mu is equal to 1 by mu delta Q by delta T. Is equation number 2. Now, C is known as molar specific heat capacity of the substance. Like S, C is independent of the amount of the substance. C depends on the nature of the substance, its temperature and the conditions under which heat is supplied. The unit of C is joule per mole per Kelvin. We can use the same law of equipartition of energy that we used there to predict molar specific heat capacity of solids. We consider a solid of n atoms, each vibrating about its mean position. An oscillator in one dimension has every energy of 2 1 by half kVt is equal to kVt. In 3 dimension, the average energy is equal to 3 kVt. For a mole of a solid, the total energy is U बराबर 3 kVt गुना Na बराबर 3 RT. Now at constant pressure, delta Q is equal to delta U plus P delta V बराबर delta U. Since for a solid, delta V is negligible, so C is equal to delta U, delta Q by delta T बराबर delta U by delta T बराबर 3R. It is shown in the table for a specific and molar heat capacity of some solid at room temperature and atmospheric pressure. In this we see that the molar specific heat capacity of carbon is very, very less. The agreement is known to break down at low temperature. A specific heat capacity of water, the old unit of heat was calorie. And 1 calorie was defined to be the amount of heat required to raise the temperature of 1 kg of water by 1 degree C. It means it was found that the specific heat capacity, specific heat of water varies slightly with temperature. In the below figure, it is shown the graph between a specific heat and temperature. Variation of a specific heat capacity of water with temperature, it is shown in the figure. Precise definition of calorie. 1 calorie is defined to be the amount of heat required to raise the temperature of 1 gram of water from 14.5 degrees C to 15.5 degrees centigrade. Heat is just a form of energy. It is preferable to use unit joule J. In its unit, the specific heat capacity of water is equal to 4186 joule per gram per Kelvin, or it is equal to 4.186 joule per gram per Kelvin, and the first is 4186 joule per kg per Kelvin. It is called mechanical equivalent of heat as J. We can use as W is equal to JH, where J is the mechanical equivalent of heat, and its value is 4.886 joule per gram per Kelvin.